So today we're doing a lab on buoyancy, and you're going to use the following equipment. You need a cylinder that's in the table, on the table in the back of the room. You need a graduated cylinder. You don't need this alcohol. I'm going to actually do part 2 of the lab. We're going to do it. We're going to do it as a group, but really I'm going to do it, and you guys are going to watch and just write down the numbers. Okay. So what we're going to do is compare the buoyant force provided by alcohol with that provided by water, and then you're going to do the experiment with water. The reason I'm going to do it and you're going to watch is because this is all the alcohol we have, and it's just not, you need a beaker full of it. So, well, I don't know, 2 groups could do the lab with the alcohol. So I'll just do it, and we'll share the results. So let's see, you also need a force probe, and you need a beaker, and you need, this is called a lab jack, and this part should be at your station. The rest of it you'll have to bring to your station. I just remind you, when you're finished with the lab, please return what you got from the table in the back to the table in the back. Okay, so what we're going to do is you're going to have a beaker full of water, partially full of water, and then on this cylinder you're going to make marks every centimeter apart. There probably are already marks on your little metal cylinder, so you can check it to see if you agree that the marks are actually a centimeter apart. That's kind of an important part of it, because what we're going to do is raise the liquid up by raising up the whole beaker sequentially, so that we're moving it up a centimeter at a time, and then we're going to read what the weight of this thing is measured as when part of it's submerged. So can you tell me what would happen if I were hanging from a scale and the scale was suspended from the ceiling, and then if a giant started lifting a swimming pool up higher and higher, so I was more and more underwater, what would the weight on the scale read?
Less.
Less. And why?
Because of the water pressure?
It is because of the water pressure. It's because, and this is in the pre-lecture, or will be as soon as I get it recorded. I've got it in the PowerPoint, I just haven't had time to talk through it yet. But the farther down underwater you are, can you tell me what kind of pressure you feel?
Greater.
Greater pressure. If you've ever done any diving or swimming, you know that when you're, say, 5 feet underwater, you can definitely feel more pressure on your ears. And that's because fluid pressure depends on how deep you are in the fluid. So, and you guys, you kind of have a sense of that, because you know they have like these underwater diving bells. If you're going to go way down near the floor of the ocean, you have to have a special pressurized helmet thing around you, maybe even an entire vehicle, a little pressurized vehicle, because the water pressure at those depths is so high. So it turns out, because the water pressure at a low place is higher than the water pressure at a high place, that there's a different force pushing down and up, and the greater force is pushing up. We'll talk more about that in class. But for now, I guess the main things I want you to realize, and I wonder, would it even be better for me to just show you part of the slide on PowerPoint? I think it might be more efficient here. I would like to be able to get you as quickly as I can because I know that, I just know that everybody's exhausted. I know I am. Can you see that? I'll pull the screen down just a sec. All right, so it's called Archimedes Principle, and what Archimedes Principle says is that, well, first of all, let me show you. This is what I was talking about. So the liquid pressure, if you've got a cube that's completely submerged, the water pressure pushing up on it on the bottom surface is greater than the water pressure pushing down on it at the top. Because the water pressure only depends on the depth, the height of the fluid above it. So that's what causes this thing called the buoyant force. And rho GV, that turns out to be the pressure, or the weight, I'm sorry, of the fluid that gets displaced. Rho is called the weight density, or the mass density. G is the acceleration due to gravity, and V is the volume of the water that gets displaced. But here's the, we're not really going to look at the reason behind this, but we're going to investigate this idea right here. The buoyant force is the weight of the displaced fluid, okay? The buoyant force is the weight of the displaced fluid. So if you push a certain amount of water out of the way, the buoyant force on you is going to be equal to the weight of that water, okay? Now when you float, you push away water equal to your weight, and when you sink, you push away water equal to your volume, but really we don't even need to worry about that. But objects sink if their density is greater than the density of the fluid, and they float if it's less. Okay, we don't need to worry about that. So that's all we need to worry about here. So what we're going to do is launch Logger Pro, and you can see it's reading the force. They read to 3 decimal places, but I'm not sure how much I believe that. You want to, nonetheless, that's all we've got. I want you to be on the 10 Newton scale, and the first thing you're going to do is zero the force probe. Let's see, is one of these 0? Do you see, do you guys know? Is that 0? I thought there was oh, there, is that 0? Yeah, set the 0 point. Can you see where it's right next to the collect button? So I just want to tell the computer that that's 0. Now you see what, it's so sensitive or unstable. Maybe unstable is a better word. So, it's reference 0, okay? And even though it's giving you a number to 3 decimal places, you can't even really trust the second decimal place, I don't think. But go ahead and write down what you see. Just take the value with a grain of salt. So let's. I'm going to put some alcohol in this beaker, and the table that I want you filling out right now is on page 71. The last column, apparent weight in alcohol. Okay? The first reading we're going to make is the apparent weight just in the air. And I don't want to fill it up to the brim, because if I do, then it's going to overflow when I get the cylinder completely immersed. Okay, so let me lower the lab jack a bit here. So nothing is underwater. So the first reading we're going to make is apparent weight in alcohol, when the submerged depth is 0. It's not down there at all. And here's what we're going to do. We're not just going to look at these numbers down here. We've used this technique before. We're going to collect data for 10 seconds, and you can see it's kind of constant. Yes, you're seeing that happen? Are you aimed at the computer screen? You might show.
I'm sorry.
That's okay. So now, when you collect data, then you go to stat, and do you remember doing that? It gives you the mean value, the minimum, and the maximum.